Hello and welcome to comp452 computer architecture. So let's begin building the data path. We want to build this data path to implement the instructions that we want our processor to execute. Okay, so let's write here. Let's build data path. Okay. So what is the first step that we want to do? We want to fetch instruction. We want to fetch instruction and update program counter to point to the next one. Okay, that's what we want to do. Okay, so this is our instruction memory. And this is our program counter register. So program counter register presents the address of instruction to instruction memory, and then instruction memory will bring out the instruction code at that location. Now we want to update program counter. So we update program counter by adding 4 to it, because we know the next instruction will be at the current value of program counter plus 4. So we want to do an addition operation. So we use the same ALU, but we hardwire that ALU to perform addition. So this is hardwired 4. Hardwired 4 goes into the top input of this adder, and this program counter value, current program counter value, it goes into the second input of this adder. Okay, so let me draw a better figure, and so let's write ADD. This is simple adder. So we get PC plus 4 as output of this adder. We reroute it and we feed it to program counter. So this was the address and this was the instruction code. 32-bit instruction code. Okay, so what is the size of this line? 32 bits. This is 32 bits. This is 32 bits. 32 bits. 32 bits. Okay, and obviously we know that this is also 32 bits. So we have fetched the instruction and we have updated the program counter. Alright, now let's for the time being, let's focus our attention on R-type instructions. Let's focus our attention on R-type instructions. Okay, so if it's an R-type instruction, you know that it will require reading two registers values, two register values. Okay, so those two register numbers, we provide two register numbers to the register file. And if you remember, this was our register file that we constructed in appendix B. So this was read register 1. I'm just going to write it read 1. This is read 2. This is write register number, and this was the data to be written to a register. Okay, now instruction code, if you look at the format of the instruction code, and I'm sure you are very much familiar with it, first 6 bits are opcode, then RS, then RT, then RD, then shift amount, and then function code. Let's stop for a minute for Azan. Alright, we're back. So this is bit 0 to 5, this is bit 6 to 10, 11 to 15, 16 to 20, 21 to 26, 25, and 26 to 31. So bit 21 to 25 will go here, bits 16 to 20 will go here, and bits 11 to 15 will go here. Okay, so this is 32-bit word. Of these bits, 16 to 20, no, 21 to 25, 21 to 25 go here, 16 to 20 go here, and 11 to 15 they go here. And this is the data line. We'll talk about this in a minute. Now once this happens, this register file will present two numbers at its output. This will be the value of RS register, This will be the value of RT register. Okay, now these two values will go to the inputs of ALU, our main ALU. Okay, this is our this is our main ALU, and main ALU will have 4 lines, control lines, that will determine the operation that needs to be performed, and ALU will produce an output result Okay, and this output result will be routed back to the data input of register file. So let's write here that this is reg file, register file. I'll show you the neatly drawn figure PDF once we are done with this hand drawing. Okay, so now you see, for example, we have add 4, 5 and 6. This is just an example. So this is RD register, this is RS register, this is RT register. So let's see what goes to various inputs. So RS register value comes here. RS register number comes here. Sorry, not value, number. It's a 5-bit number. So this is 5 bits, this is 5 bits, this is 5 bits. So what do we get here? 0, 0, 1, 0, 1. This is 5. Actually, 0, 0, 1. Sorry. 0, 0, 1, 0, 1. This number comes here. Okay. RS register number. RT register number is 6, which is 0, 0, 1, 1, 0. So here we get 0, 0, 1, 1, 0. And RD register is, the register number is 4. So here we get 0, 0, 1, 0, 0. Okay. Now here, let's suppose that the value in RS, suppose that value in register 5 was 0 hex 0, 0, 0, 0, 0, 0, A, B, and the value in register 6 was 0x 0, 0, 0, 0, 0, 0, C, D. So what do we get here? We will get here 0, 0, 0, 0, 0, 0, AB. This is 32-bit value. And what do we get here? The register file will produce 0, 0, 0, 0, 0, 0, C, D here. Now these two numbers, this number and this number, they will go to the input of the ALU, and these 4 lines, actually these 4 lines, they will instruct the ALU to perform addition on its input values, and the result of that addition will come here. This will be a 32-bit number, and it will be rerouted back to the data input of register file. Now you see that we have presented 0, 0, 1, 0, 0 to the right reg number, right reg input. So the data that comes here, the 32-bit data that comes here, will be written to register number 4. Now we have to keep in mind that there is going to be a right register control signal, right reg control signal here, and this right reg control signal will be asserted so that the data gets written to the destination register RD. Okay, so if we simply look at this diagram, our our uh, our data path is complete for R type instructions. So for R type instructions, our data path is complete. Only data path. We are not talking about the control path yet or control signals yet. Okay. So look what we are doing. We are presenting the program counter value to instruction memory. Okay, instruction memory, this, and then we are updating the program counter by adding 4 to it, and we reroute the next value, the updated value of program counter back to the program counter register input. Instruction memory presents us the instruction code, and this instruction code has various fields, and we are right now talking about the R type instructions. So, and in the R type instructions, we are talking about add, subtract, and, or, nor, and SLT. These are the 6 instructions that we want our processor to execute. So for these 6 instructions, our S register number goes to the read 1 port, our T register number goes to the read 2 port, our D register number goes to write reg input. Once this happens, the register file presents you with the contents of RS register, which is 5 in this case, and we are assuming that it contains 000000AB, and the other one contains 000000CD. So these two 32-bit numbers go to the two inputs, the top input and the upper input and the lower input of the main ALU. Main ALU is instructed to perform addition operation by using these 4 control lines, and the result produced is also 32 bits, and it is rerouted back to the data input of the register file. Actually, we call this write data. We don't call it data input, we call it write data. Write data. Actually, I understand this figure has become very messy, but I'll show you the neatly drawn figure once you're done with this portion. Okay, so with this we have completed our data path for R type instructions: add, subtract, and, or, nor, and SLT. Okay, so our next part will be extending the data path for I type instructions. Extending the data path for I type instructions. Okay, so with this we stop this part of the lecture. There we go.